Okay, students, let's start with today's topic, that is A2 physics, topical past papers, and the name of the chapter is quantum physics. So, this is your chapter number 11. Let's get started with our past papers or chapter number 11. So, let's move on to question number 1. A photon has an energy of this. Okay, this is the energy of photon. Calculate the momentum of the photon. We need to calculate the momentum P of the photon. We are given the energy E. So you might remember that energy of a photon is equals to what? Momentum into the speed of light, that is C. You have to calculate momentum P here. What can you do? Energy divided by the speed of light is equals to your momentum. What is energy? 3.11 into 10 raised to the power of minus 19. What is the speed of light? 3 into 10 raised to the power of 8. What will your momentum come out to be? Let's calculate it. 3.11 into 10 raised to the power of minus 19 divided by 3 into 10 raised to the power of 8. This comes out to be 1.04 into 10 raised to the power of minus 27 is your momentum of the object, you can say, of the photon basically. A laser beam has a power of this. Okay, you have a power of this. The light from the laser has a wavelength of this. Okay, now you have the wavelength as well and power as well. Okay, determine the number of photons. Okay, you have to calculate the number of photons emitted by the laser in a time of 1 second. Okay, so from AS level physics, you might remember power is equals to energy over time. What is the power? 350 into 10 raised to the power of minus 3. What is the time? 1 second multiply by 1. What will your energy come out to be? 350 into 10 raised to the power of minus 3 joules. Okay. This amount of energy is supplied by the photons. This amount of energy is supplied by the photons of 640 nanometer wavelength. So what can you do? Energy is equals to HF. This is for one photon. If I want to calculate how many photons were there, I will put a n here. That is the number of photons. What is my energy? 350 into 10 is the power of minus 3. The number of photons, I don't know. Multiplied by h, that is the Planck's constant, 6.63 into 10 is the power of minus 34. Multiplied by the frequency. I don't have the frequency. What can I do? V is equals to f lambda. Velocity divided by lambda will be placed in place of frequency. So what is your C? 3 into 10 raised to the power of 8. What is your lambda? Your lambda is 640 nanometers. If you observe this entire equation, only n is an unknown variable. So you only don't know about n. You can easily calculate that. Rearrange this equation. 350 into 10 raised to the power of minus 3. Multiply this to the other side into 640 10 raised to the power of minus 9 divided by 6.63 into 10 raised to the power of minus 34 multiplied by 3 into 10 raised to the power of 8. You will get your answer for the number of photons. What does your answer for number of photons come out to be? It comes out to be 1.1 into 10 raised to the power of 18. Let's further move ahead. The laser beam is incident normally on a surface that absorbs all of the photons. Okay, show that the force exerted on the surface by the laser beam is given by this formula. Okay, we have to show that force is equals to power over the speed of light. We have to show this. Okay, how will we start this question? Very, very easy. From AS physics, although this is an A2 question, but it utilizes some of AS physics. From AS physics, we know that force is equals to change in momentum over time. Okay. In place of momentum, what can I write? I have told you guys in the first part, in place of momentum, what can I write? Energy over the speed of light. So let's replace it here. Energy over the speed of light. In place of time, what can I write? Yes, in place of time, what can I write? I can say power is equals to energy over time. Can I make time the subject here? Yes, energy over power is equals to my time. So in place of time here, I can substitute what? Energy over power. Let's do that. Energy over power. What will happen? Energy and energy will get cancelled out. Power will come in the numerator. Force is equals to power over the speed of light. Hence, we have shown this result. Hence, we have shown this result. Let's further move ahead. Light of a single wavelength is incident on the surface of different metals. Okay. The work function energy of the metals is given in table 7.1. Okay, these are the work functions of different metals. Okay. Explain the term threshold wavelength. What is threshold wavelength? Maximum wavelength that causes an emission of electron. That causes an emission of electron. Simple as that. Let's move on to part I2. For the metals in table 7.1. Okay, for the metals in table 7.1, calculate the value of the largest threshold wavelength. Now, there is a smart way to do this question, and there is a like very absurd way to do this question. You have to calculate the largest wavelength. You have to calculate the largest threshold wavelength. First of all, let's write the formula of energy of a photon. Energy of a photon is equals to hc over lambda. Okay, can you see here that lambda is inversely proportional to energy? Or in this case, you can say, let's say this is the work function. Let's say we write it like this. Work function is equals to hc lambda naught. Okay. Can you see work function is inversely proportional to lambda naught? Yeah, that's correct. So for the largest threshold wavelength, we will have the smallest work function or phi. We will have the smallest work function or phi. Which element or metal has the smallest work function? Potassium 2.26, and the units are in electron volts. Okay, so let's write here 2.26 into 1.6 into 10 raised to the power of minus 19, because energy is in electron volts. What is the value of H? 6.63 into 10 raised to the power of minus 34. What is the value of C? 3 into 10 raised to the power of 8. Okay, can you calculate lambda naught? Yes, very, very easy. Just rearrange the formula. Lambda naught is equals to 6.63 into 10 raised to the power of minus 34 into 3 into 10 raised to the power of 8 divided by 2.26 into 1.6 into 10 raised to the power of minus 19. You can easily calculate your lambda naught, which comes out to be 5.5 into 10 raised to the power of minus 7 meters. You can place your answer here. Let's move on to the next question. The marking schemes are attached in the PDF. You can download it from the link in the description below. Let's move on to the next question. State what is meant by a photon. Photon is a of energy, packet of energy of what? Packet of energy of electromagnetic radiations. Photon is a packet of energy of electromagnetic radiations. Okay, let's see part B. When the surface of a metal is illuminated with electromagnetic radiations, electrons are sometimes emitted from the metal. Okay, state the name of this phenomena. What is this phenomena known as? Photoelectric effect. Photoelectric effect. Simple as that. Let's move on to part I2. It is observed that this phenomena occurs only when the frequency of radiation is greater than a minimum value. Okay, this will only occur when the frequency will be greater than the threshold frequency. Okay. Regardless of the intensity of the radiation. We have studied this in theory, exact same thing. Explain how this observation provides evidence for the existence of photons. We have to explain how this observation that electrons are only emitted above a specific frequency and increasing the intensity doesn't have any effect. How does this provide us evidence that evidence that photons exist? Okay, how will we do this? Okay, so you can start this answer by saying that electrons require a minimum energy, a minimum energy to escape. Okay, electrons require a minimum energy to escape. Okay, this energy, this energy is provided. This energy is provided by absorbing by absorbing photons. This energy is provided by absorbing photons. Hence, or you can say, moreover, this energy, moreover, the energy of photons is directly proportional to frequency, is directly proportional to frequency, proportional to frequency. Hence, Hence, if you increase the frequency above the threshold frequency, then only your electrons will be emitted. This verifies the existence of photons. And increasing the intensity does not increase the emission of electrons. Why? Because intensity of photons basically means what? Sorry, intensity of radiation, you can say, because here in the question radiation is written. Intensity of radiation means the number of photons incident on the metal, I guess. Is there any? You can say on the metal. Okay, let's further move ahead. Let's move on to part C. Figure 8.1 shows the variation of the maximum kinetic energy. Okay, maximum kinetic energy versus frequency graph is given to you. Okay. State the name of the quantity represented by the gradient of the light. Okay, what have we studied? If we plot maximum kinetic energy on the y-axis and frequency on the x-axis, the gradient of this line will be equal to what? Planck's constant. The gradient of this line will be equal to what? Planck's constant. So let's write it here. Let's write it here. Planck's constant. Simple as that. And do you guys remember? Do you guys remember what used to be the y-intercept of this line? What used to be the y-intercept of this graph? Like, let's say if I extend this here, what used to be this point? What used to be this point? This point used to be the negative work function. So you can write it as well. This will be your negative, or you can say negative work function. Simple as that. Let's further move ahead. Let's move on to the next question. Show that the momentum of a photon of electromagnetic radiation with a wavelength lambda is given by this. Okay, we have to show that momentum of a photon is given by this equation. How will we do this? Any ideas? Okay, we know one thing, that energy of a photon is equals to what? Hc over lambda. We also know that energy is equals to P over C. Yeah, let's equate both these equations of energy. This was the first equation of energy. This is the second equation of energy. Let's equate both of them. Hc over lambda is equals to Pc. C and C gets cancelled out. Momentum is equals to H over lambda. Simple derivation. Let's move on to part 2. Use the expression in part I1 to show that the photon in free space that has a momentum of this is a photon of red light. Okay, let's utilize this equation. P is equals to h lambda. Your momentum is what? 9.5 into 10 raised to the power of minus 28. Your h is 6.63 into 10 raised to the power of minus 34 divided by lambda. What will your lambda value come out to be? Lambda comes out to be 700 nanometer, which is wavelength of red light. Which is wavelength of red light. Let's further move ahead. A beam of red light of intensity this, okay, this is your intensity, is incident normal on a plane mirror as shown in figure 8.1. Okay. The momentum of the photon is this. This is the momentum of the photon. This is your intensity. Okay. Let's further move ahead. All of the light is reflected by the mirror in the opposite direction to its original path. The cross sectional area of the beam is this. Okay. Show that the number of photons incident on the mirror per unit time is this. Okay. We have to calculate the number of photons per unit time. Okay. So first of all, let's calculate the power here. Power had a formula of what? Intensity into area. We have studied this in AS. What is your intensity formula? 160. Sorry, what is your intensity value? 160. What is your value of area? Your value of area is 2.5 into 10 raised to the power of minus 6. 2.5 into 10 raised to the power of minus 6. Let's calculate this answer. This comes out to be 160 into 2.5. This is 400 into 10 raised to the power of minus 6 volts. Okay. Can I calculate the energy? Yes. Since it is per unit time, we have to calculate the energy for 1 second. So power is equals to energy over time. Power is this, time is 1. 400 into 10 is the power of minus 6 joules is your energy. Okay. Now what can I do? This is very similar to a question that we have done earlier. Energy is equals to what? N and Hc over lambda. What is N? N is the number of photons. What is Hc over lambda? It is the energy of one photon. Let me mark it here. This N is number of photons. And this Hc over lambda is what? Energy of one photon. Simple as that. Okay. What is the total energy? 400 into 10 raised to the power of minus 6 is equals to N. What is the value of H? 6.63 into 10 raised to the power of minus 34. What is the value of C? 3 into 10 raised to the power of 8. What is the value of lambda? Have we calculated lambda earlier? Yes, 700 nanometers. So let's place it here. 700 into 10 raised to the power of minus 9. If you closely observe, only n is missing in this question. Only the value of n is missing in this question. Can you calculate it with this entire equation? Yes. The value of n comes out to be what? 1.4 into 10 raised to the power of 15. This is what we had to show. This is what we had to show. Let's put it in a black box. Something like this. Yeah. So, yes, let's move on to part I2. Show that the pressure exerted by the light beam in the mirror is okay. We have to calculate pressure. So, let's start with the basics. Pressure is equals to force over area. Okay, pressure is equals to force over area. How can I represent force? How can I represent force? Force from AS level we know is what? Change in momentum over change in time divided by area as usual. Now, how will I calculate change in momentum? How can I calculate change in momentum? Yes, if you closely look here, the beam of light was carrying photons towards the right with a momentum of what? 9.5 into 10 is the power of minus 28. And if you see further, they are reflected back in the opposite direction. They are reflected back in the opposite direction. So they are reflected with the opposite direction momentum of the same value. 9.5 into 10 is the power of minus 28. The photons were hitting with a momentum of 9.5 into 10 is the power of minus 28 towards the right. This was towards the right. And after hitting the plane mirror, they are getting reflected back with a momentum of what? 9.5 into 10 is the power of minus 28 towards the left. You can say this is your initial momentum. You can say this is your final momentum. Can you calculate change in momentum? Yes. Yes. Before doing that, let's assume that the left hand side is positive and the right hand side is negative. Final momentum minus initial momentum. Your final momentum is towards the left, hence it will be positive. So this becomes 9.5 into 10 is the power of minus 28. Your initial momentum is towards the right, so it will become negative. Okay, negative 9.5 into 10 is the power of minus 28. Okay, negative negative becomes positive. 19 into 10 is the power of minus 28. This is your change in momentum. But there is one more problem here. There is one more problem here. Can you see there are 1.4 into 10 raised to the power of 15 photons? The number of photons is what? 1.4 into 10 raised to the power of 15. You have calculated the change in momentum for 1. This is the change in momentum for 1 photon. Okay. What will we do to calculate the change in momentum for all the photons? We will say that the change in momentum for one photon was 19 into 10 raised to the power of minus 28 as far as I think. Yeah, 19 into 10 raised to the power of minus 28. And the number of photons is what? 1.4 into 10 raised to the power of 15 divided by area. What is the value of area here? 2.5 into 10 raised to the power of minus 6. Let's divide it 2.5. 10 raised to the power of minus 6. What will your answer for pressure come out to be? Your answer for pressure comes out to be 1.1 into 10 raised to the power of minus 6 pascals. Simple as that. Let's see part C. The beam of red light is now replaced with blue light. Okay. Now the red light is replaced with blue light of the same intensity. Okay. Suggest and explain whether the pressure exerted on the mirror by the beam of blue light is same, less, or greater than the pressure exerted by the red light. Okay. Now here you have to think in two dimensions. Okay. See, pressure is equals to what? Force over area. Okay. And if I further break this down, pressure is equals to what? Change in momentum over change in time divided by area. Okay. Now, if you are just a base level thinker, if you don't think a lot, you will say that momentum is equals to h lambda. Okay, since wavelength of blue light is less than the wavelength of red light, since wavelength is decreasing, momentum will increase. Okay, that's correct up till now. That's correct up till now that you will have a greater momentum. Why? Because wavelength and momentum are inversely proportional. But you have forgotten one important thing here. You have forgotten one important thing here. See, energy is equals to NHC over lambda. Energy is equals to NHC over lambda. Okay. If you closely look here, energy will be constant. The amount of energy will be constant. The amount of energy produced by the photon will remain constant. Okay. And H is also a constant. That is the Planck's constant. C is also a constant. Yes. If you rearrange this formula, if you somehow rearrange this formula, this will become something like this. Lambda is equals to n hc over e. Okay. Okay, this is your formula after rearranging it. Now you know this entire thing is constant. So you can replace it by a direct proportionality sign. You can say lambda is directly proportional to the number of photons. Now, if you closely see here, by decreasing the wavelength, what are you doing? By decreasing the wavelength, what are you doing? You are decreasing or reducing number of photons. You are reducing number of photons. What does this mean? If I break this pressure formula further, this was what? Momentum into the number of photons divided by time divided by area. I have bring this area towards the denominator. If you see, although momentum is increasing, you are correct. Due to the decrease in wavelength, momentum is increasing. But due to the decrease in wavelength, what else is happening? The number of photons is also decreasing. If one quantity is increasing, the other quantity is decreasing. What will happen? Pressure remains same. Pressure remains same. Simple as that. Let's further move ahead. This was a very good question. Okay, so let's move on to this question. Figure 8.1 shows the lowest 4 energy levels of an electron in an isolated atom. Okay, so these are the 4 energy levels of an electron. Okay. Figure 8.2 shows the lines in the emission spectrum of the atom that corresponds to the transition of the electron from n is equals to 3 to n is equals to 1 and from n is equals to 4 to n is equals to 1. So basically these frequency lines, these two lines are the emission spectrum. Okay, and how was this formed? Let's say you were transitioning from a 4 level to 1 level. Okay, let's say your electron was jumping from a energy level of 4 to energy level of 1. What will it do? It will emit a photon in the process. This photon will have some amount of energy, and energy is equals to hf. So this photon will carry some amount of frequency. Then you suppose that your electron jumped from n is equals to 3 to n is equals to 1. Due to this transition as well, you will emit a photon that will carry energy, and this energy will also be equal to hf. Can you see this blue energy is lesser? Hence the frequency here will also be less. So I can say that this line, the lesser frequency line, is from 3 to 1. This is for the transition from 3 to 1. This one. Oh, let me write it like this. This line is for the transition from 3 to 1. And this line is for the transition from n is equals to 4 to 1. Okay. Let's further read it out. Explain with reference to photons why there is a single frequency of electromagnetic radiation that corresponds to each of these transitions. Very, very easy. You can say energy of photon is equals to what? Is equals to the energy difference between electron energy levels. Okay, energy levels. And for the second marks, you can write the energy of photon, the energy of this photon, you can say, is directly proportional to frequency. Simple as that. Nothing complicated here. Okay, let's further move ahead. On figure 8.2, draw a line that corresponds to the transition of the electron from n is equals to 2 till n is equals to 1. Label this line as A. Okay. Now let's say you are going from n is equals to 2 to n is equals to 1. You will notice that this energy is way lesser than both of the previous energies. Hence the frequency here will also be less. You will draw a line that is of a lesser frequency here. And let's label this as line A. Okay, let's move on to part I2. On figure 8.2, draw the line that corresponds to the transition from n is equals to 2 from n is equals to 3 to n is equals to 2. Label this line as B. Okay, let's first of all see what the examiner is asking. Okay, so we have to transition from n is equals to 3 to 2. This energy is further lower. This is the lowest energy. So this will also have the lowest frequency. We will draw it further towards the left, something like this. Let's say this is your line B. Okay, let's further move ahead. The frequency of radiation represented by line A is Fa. Okay, the frequency of radiation or photon represented by line A is Fa. The frequency of radiation represented by line B is Fb. Okay. The ground state has an energy of E1. Okay. Derive an expression in terms of Fa, Fb, E1 and Planck's constant for the energy E3 at n is equals to 3. So let's see what the examiner is asking. The examiner is saying that at this ground level your energy is E1. You have to calculate the energy at this point. Okay. And you know that this transition from n is equals to 2 to 1 is releasing an energy that is equals to HFA, because the frequency of emission for the first line A was Fa. And you also know that this transition is releasing an energy of what? HFB. Okay. If you sum up all these energies, it will be equal to E3. E3 is equals to E1 plus HFA plus HFB. Let's take H as common. E3 is equals to E1 plus HFA plus FB. Simple as that, nothing complicated. Let's further move ahead. Let's further move to the next question. Okay, now let's move on to the next question. State what is meant by de Broglie's wavelength. So de Broglie's wavelength is the wavelength associated with a moving particle. Associated with a moving particle. Simple as that. Let's further move ahead. Figure 7.1 shows a glass tube in which electrons are accelerated through a high potential difference to form a beam that is incident on a thin graphite crystal. Okay, this is your graphite crystal. If someone is wondering what is the graphite crystal, okay, then what is written? After passing through the graphite crystal, the electrons reach the fluorescent screen. The screen glows where the electrons strike it. Okay, so the screen is glowing in this part. Okay. Figure 7.2 shows the fluorescent screen viewed end on from the right hand side. So this is the pattern forming on the fluorescent screen. We have already seen this in the notes. and the lectures. Okay. State the name of the phenomena illustrated by the pattern. So what is happening? Electron diffraction is happening. Okay. Explain what can be concluded from the pattern in figure 7.2 about the nature of electrons. Okay. So this pattern tells us two things, that electrons are diffracting. And there is one more thing that this pattern tells us. There are black lines which tell us that constructive interference is happening, and there are these empty spaces which tells us that destructive interference is happening. So you can say that electron undergoes interference as well. Undergoes interference. Both of these things tells us what? Both of these things tells us what? Electron or electrons behave as waves. Simple as that. Let's move on to part C. The electrons in B are now accelerated through a greater potential difference. Okay, so your V has increased. Okay, between the cathode and the anode. Sketch the pattern that is now seen on the fluorescent screen. We have also discussed this in the notes. We know that lambda is equals to h over momentum. And we also know that momentum is equals to what? 2mvq. So lambda is equals to h over 2mvq. If your V or voltage is increasing, what will happen to your lambda? It will decrease. And as your lambda decreases, what will happen? Your circles will shrink in size like this. Something like this. Okay. Explain with reference to de Broglie's wavelength the change in the pattern of the fluorescent screen. We have just done that. You can also write it in words. A greater potential difference results in greater momentum. Okay, momentum, one second, momentum, and a greater momentum, I am just writing P for momentum now. Okay, a greater momentum leads to a smaller wavelength, or you can say lambda. And if your wavelength becomes smaller, what will happen? Your diffraction angle will decrease. If wavelength decreases, angle of diffraction will decrease. Angle of diffraction will decrease. Simple as that. Let's move on to the next question. I think the same is written, yeah, in the marking scheme. Yes. Okay, let's move on to this question. I have already pre-written this answer because this was a lengthy answer and I didn't want it to waste your time. So let's see this question. A beam of white light passes through a cloud of cool gas. The spectrum of the transmitted light is viewed and contains a number of dark lines. Explain why these dark lines occurs. So what can you say? As light passes through the cool gas, or you can say cold gas, photons get absorbed by the electron. And these photons have an energy equal to what? The energy difference between the electron energy levels. And this photon ki energy is equals to a specific wavelength or frequency. Hence, the specific frequency or wavelength of photons that get absorbed gives a dark line on the spectrum. After some while, the electrons get de-excited and they emit the photon in all directions with a reduced intensity. Some energy levels for the electron in a hydrogen atom are illustrated in figure 7.1. Okay, so these are some energy levels illustrated for an hydrogen atom. Okay. Table 7.1 shows the wavelength of photons that are emitted in the transitions to n is equals to 2 from the other energy levels. Okay, so basically we are coming to 2 from all the energy levels, from 6 as well, from 5 as well, from 4 as well, from 3 as well. So these are the 4 transitions that will happen. From n is equals to 6 to 2, from n is equals to 5 to 2, from n is equals to 4 to 2, and from n is equals to 3 to 2. So accordingly I should have 4 wavelengths and I have 4 wavelengths. The energy associated with the energy level 2 is negative 3.4. Okay, so this energy is negative 3.4 electron volts. Okay, you have to calculate the energy at n is equals to 3. You have to calculate the energy at n is equals to 3, E3. Okay, how will you do that? Okay, you know that E3, we have also done this question previously but in a numerical format. You know E3 is equals to what? E2, that is 3.4 multiplied by 1.6 into 10 raised to the power of minus 19. Why have I done that? To convert this electron volts into joules. Plus, what will I do? I will add the energy of photon emitted when we go from 3 to 2. Okay. Now, here is one more question for you guys. The energy difference here when you go from n is equals to 3 to 2 is the lowest. Okay. If I write the formula of energy, energy is equals to hc lambda. If your energy difference from 3 to 2 is the lowest compared to all the other energy levels, your lambda will be the highest. So which wavelength will you use here? 658. You will use a wavelength that is equals to 658. So let's use that and add up the energy here. So your energy will be equal to 6.63 into 10 raised to the power of minus 34. Your c will be the speed of light divided by lambda, that is equals to what? 658 into 10 raised to the power of minus 9. Your energy comes out to be minus 2.42. Let me 1 second, just give me a minute. I have done one error in the calculation, so let me correct it. Plus 6.63 into 10 raised to the power of minus 34 into 3 into 10 raised to the power of 8 divided by 658 into 10 raised to the power of minus 9. This comes out to be negative 2.42 into 10 raised to the power of minus 19 joules is your answer. Simple as that. Let's move on to the next question. State what is meant by the work function of a metal. So minimum energy of photon required to cause an emission of electron, with negligible kinetic energy, simple as that. Let's move on to part B. Ultraviolet radiations of frequency this are incident in a vacuum on a metal surface. The power of radiation incident on the surface is this. Okay, so this is the power, this is the frequency. Photoelectrons are emitted with a maximum kinetic energy of this. Okay. Determine the number of photons incident on the surface per unit time. So we have to calculate n, basically we have to calculate n. Okay, what can you do here? First of all, you know the power. Can you calculate energy? Power is equals to energy over time. We have to calculate per unit time. So time equals to 1. And hence energy will be equal to what? 8.36 into 10 raised to the power of minus 3 joules. Okay. Now you can equate this energy to what? NHF. What is N? Number of photons. We have also done this previously. What is HF? Energy of one photon. Okay, so let's just plug in the values here. Energy is equals to what? Energy is equals to 8.36 into 10 raised to the power of minus 3 is equals to capital N. What is the Planck's constant? 6.63 into 10 raised to the power of minus 34. What is the frequency? 1.36 into 10 raised to the power of 15. Okay, let's calculate N. 8.36 into 10 raised to the power of minus 3 divided by 6.63 into 10 raised to the power of minus 34 into 1.36 into 10 raised to the power of 15. Okay, so your answer comes out to be 9.27. N is equals to 9.27 10 raised to the power of 15. Let me also verify it with the marking scheme since we have the luxury to do that. Yes, it's correct. Yes, it's correct. So calculate the work function of the metal. Okay, you have to calculate the work function of the metal. What have we studied? Energy of a photon is equals to the work function plus the kinetic energy Maximum. What is the energy of a photon? Planck's constant 6.63 into 10 raised to the power of minus 34 into the frequency. What was the frequency here? 1.36 into 10 raised to the power of 15. 1.36 into 10 raised to the power of 15 is equal to the work function plus what was the kinetic energy? 3.09 into 10 raised to the power of minus 19. 3.09 into 10 raised to the power of minus 19. Okay. So let's calculate this answer by 10 raised to the power of minus 34 into 1.36 into 10 raised to the power of 15 minus 3.09 into 10 raised to the power of minus 19. This comes out to be 5.93. 10 raised to the power of minus 19 joule. Let's also check this from the marking scheme. Okay? So yeah, this is also correct. Okay, let's see part C. The frequency of the radiation incident on the surface is increased while the power remains constant. Oh, very good, very good. The frequency is increased while the power is remaining constant. State and explain the change of this effect on the maximum kinetic energy of the photoelectrons. What will happen? If frequency increases, what will happen? The energy of photon increases and work function phi remains constant and hence kinetic energy increases. Okay. What will happen to the rate of emission of photoelectrons? This is a very good question. Very, very good question. Only A star students will be able to do this. Only A star students will be able to do this. Okay. What will happen to the rate of emission of photoelectrons? Okay. Just pay attention. Just pay attention. Your power is constant. That means your energy will be constant. Okay. If your energy of all the photons, this is the energy for all photons. If your energy for all photons is constant, and what was the formula for energy of all photons? E is equals to capital N HF. Okay. If your energy for all photons is constant and your frequency is increasing, or let's do one more thing. If your energy is constant, because you know power is constant, and let's bring this HF to the downside. Let's make it like this. E HF is equals to N. Okay. This energy is also constant. This Planck constant is also constant. What can you do? You can say 1 over frequency is inversely proportional to N. What is N? Number of photons. If frequency is increasing, number of photons will decrease. This was a very tricky thing that most of the students didn't realize in the paper. So number of photons, you can say number of photons decreases. Hence rate of emission. Hence rate of emission of electrons or photoelectrons. Rate of emission of photoelectrons decreases. Simple as that. This marks the end of the past papers for quantum physics. If you have any confusions, still you can ask in the comments below. Thank you for watching.